Okay, today's lesson is starting a new section on service design and queuing, and certainly we'll talk about this in greater detail. Two lessons in this section. Today we'll talk about mainly single server queuing systems, and in the next lesson we'll talk more about multiple server queuing systems. So we'll dive in. Again, this is on pages 189 to 215 out of your textbook. And again, all of this will be expanded there if you can, as you read the pages, and will be expanded over what is presented here. And for today, for this lesson, we're talking about three main things. Is we're going to understand quantitative tools, understand characteristics of the service process. We will, as an example in the second part of this lesson, calculate basic operating characteristics, and we'll talk about those in greater detail. And then most importantly, we will be able to analyze waiting line systems and recommend alternatives and improvements to these systems. So let's talk about services. There are different types of services. First of all, they are pure services, things where you receive things that are not tangible. So in other words, these are things like lawyers or financial services where it's an intellectual property or intellectual products, more so than tangible things that you would purchase in a store. Others can have inputs that are consumables, such as restaurants and repairs, and often customers are involved in production. Again, if you think about a cafeteria style dining, or a department store, customers serve themselves and to a great degree. And then lastly, things that are different about services is that a service may provide a change in the state utility. So in other words, you take your automobile to a repair shop, it goes in, it's not working, and it comes out and it is working. So the state of your automobile has changed. Or again, in your lawn needs mowing. The gardening service comes in, cuts the grass, so the grass is one length before and a different length after. That's a state change or state utility. Again, pages 195 to 197, services, as we mentioned before, are intangible. And again, those things like that are idea-based or intellectually based. Service output is variable. In other words, again, in a food service industry, the menu items that are purchased are not always the same. High customer contact. Services are often perishable. They wear out, run out. The delivery and the service itself are inseparable, dispersed. Services are often more easily consumed and can be easily emulated or easily copied. So all of these things are characteristics of service. And again, here on pages 195 to 197, you would see a greater explanation of these issues. So often in service industry, waiting lines or lines are needed or formed in order to await the service that's involved. A couple that we'll think about a good deal are things like a bank, a teller, coffee shop, post office services, and in amusement parks, those types of things where lines are formed. Things that impact how these lines are formed and how long you might have to wait in those lines we're going to need to know the arrival rate of the customers. And in every case, irrespective of the application, we're going to look at a set of customers that are going to arrive to a service location. Then the next thing is, what order are we going to serve those customers? And then for the server, whether it's an individual, a person, or a machine, how fast, what's the service rate of the servers? Then next, we need to know the probability distribution of the arrival times and service times, because this will determine to a great deal the characteristics of this waiting line process. How long and what's the customer characteristics, and what conditions will a customer perceive the service quality. One of the things I want to point out here is that we're going to use, in every case of our situation, we're going to describe the arrival rate of our customers using this parameter lambda that is going to be our arrival rate. We're going to use the Greek letter mu is going to be the parameter of the service rate for our servers. And in each case of where we're going to do our analysis, the probability distribution is going to be the exponential distribution of service times of arrival or if also we will see that this is the Poisson distribution for number of arrivals for services. And these together are called, produce what's called a Poisson process when these conditions are applied. All right, so let's move on. This is the kind of system we're going to look at today. It's called a single server system. And the way we're going to depict this is that we have one server, and the square is that represents our server. We have just one, and we have customers that are represented by the circles. The customers enter our system at the rate lambda, and again, lambda is a rate. They wait in line, and then once they receive service, they depart the system at service rate of mu. And again, this is a rate of service, not the time of service, but the rate. How many customers are being served per unit of time? All right. So in the way that works, if you were to conceive that our box here is our store, if you will, that anytime the customer is inside this box, they are considered to be in the system. A customer who's not yet arrived is not in the system, and a customer that has departed is not in the system. So again, our customers are either in line waiting or they are in service. There's only two conditions. They're either in line waiting, or they're in service. And so in this depiction, we have a single server. We'll be given the arrival rate. We'll be given the service rate. And in this case, we have N is 4. We have 4 customers in the system. Four customers are in the system. Four customers in the system. So that's our general single server case. Now, what we're going to study today is the single server system. And in the next lesson, we're going to study the multiple server system. And so what I would like for you to think about is what does the single server system remind you of? And perhaps it's a post office where there's only one person working, a grocery store perhaps where there's only one person checking out, one clerk. Whereas in this case, in the next lesson, this is going to be more like a bank teller situation where we're in a multiple server system. We still have one line where people are waiting. And this customer, the next customer in line, goes to the server that is available. It can be any one of these servers. And in this case, the number of servers is S, anything greater than 0, 1, 2, up to as many as you would ever want. And so this is a multiple server situation where there's one line, there's only one line. But the customers that are in line can go to any one of the servers based on whichever is next available. And so this is more like a bank teller, indoor bank teller situation. This is more like, if you will, a post office, and I'm sure you can think of other examples that would represent this. All right, so here's what we need to know in order to do our analysis. We need to know about the calling population. The calling population is everyone who could possibly come to our service, come to our system, or stand in our line. And for our purposes, the calling population is going to be infinite. In other words, there's no restriction on how many customers could come and actually want our service. We'll still need to describe the arrival process, as I talked about, the service process, and also we'll need to know what is the service discipline. In our case, everything that we're going to study is a first come, first served. That's what FCFS stands for. First come, first served system. So the first customer, which is most of the systems that we're used to, the first customer in line gets served next. The next thing that we're going to need is to know is what is the capacity of the queue. In other words, and again, let me pause here. The word queue is, if you're not familiar with it, is an English word, and a queue just means a line, a waiting line. It's just a line. It's the same thing. It means the same thing as if you say queue, I mean just a line, a waiting line. And so how many customers can our system accommodate waiting? And again, as with the calling population, the queue capacity has to be also infinite. or it can be assumed to be infinite. Again, as we've already seen, how many servers are we going to use, and how are the service processes completed? Is there, and for our case, we're just going to look at the case where there's just one service. There's not several services. They're not in sequence. They're not in random order. There's only one service. And that similar service is provided by how many ever servers we have. All right, now here are some management issues that we want to be concerned about. You'd want to know if you are the manager of the bank, or if you were the supervisor of the post office operation, or wherever you were, how long are your customers waiting? How busy, or what percentage of time are your actual servers actually working? On average, how many customers in the system? How many altogether? How many are in the line? And you'd want to be able to know, to control the number of servers in order to reduce the waiting time. As you all have been to a grocery store or a bank, you always think, gosh, if they had one more server, if they had two more servers, two more clerks, this would move so faster. And how do you want to reduce the waiting time, and how much does it cost to operate the system? All of these are management issues, and our managers want to be able to know, given how we operate, what's the result going to be, and what's going to be the impact on customer perception. All right, we're getting now into a little bit more details about how we're going to analyze our waiting lines. And again, here's our a representation of our single server system. And in order to do our analysis with the formulas that we're going to see, the arrival process has a known arrival rate. Now it says constant arrival rate, but that doesn't mean that. What that means is that the arrival rate does not change over time, but the number of customers and how they arrive does change. So in 1 hour, if you have an arrival rate of, let's say, and again, we're going to say lambda is 3 customers per hour. That's a rate. We could have, in the first hour, we could have 3 customers arrive. In the second hour, we might have 1 customer arrive. And in the third hour, we might have 6 customers arrive. And then in the fourth hour, let's see, we might have 2 customers arrive. And so the average arrival rate, how many customers have we had? That's we've had 3, 4, 10, 12 over 4 hours. So our arrival rate is actually 3 per hour, but that rate does not change. If this is 8 a.m. and this is 10 p.m., that arrival rate does not change over that period of time. And we have to have this process has to have the exponential distribution. Similarly, we only have 1 server, and that server, the average service rate is mu, and this is going to be expressed as, again, the number of customers. I'm going to abbreviate that, number of customers per unit of time. All right, these customers always stay in line. Once they enter the line, they stay in line. They don't leave. or renege. In other words, the person who's, let's say, customer number 2, he doesn't just decide, well, I've been here too long, I'm leaving. They don't renege, they don't balk. In other words, there's a customer here and decides, there's too many in line, so I'm going to not enter. They don't do that. Once they enter, they're staying in line, and then they don't jockey. In this case, we only have one line, but we'll see in the future the customers don't move from one line to the other. Again, the line length is infinitely long. They stand in one line, the served on first come, first serving. There's no cutting line, no service preference. So in other words, there's no priority service. Everybody enters the line, stands in line, and waits in line until they receive their service. Now here are, given these factors that we saw on that last slide, there's at least six different operating characteristics that we can tease out from these waiting lines. We'll see the formulas for these in a minute. And again, these fall into 3 general categories. We'll be able to talk about the number of customers that are in our service, the time they spend in our service, or we're going to be able to answer some probability questions about our service process and our waiting line. Now, there's 2 types of operating characteristics related to the number of customers, and we're going to call the first one L, which is going to represent the average number of customers in the system, and we're going to call the term L sub Q is the average number of customers in the line. And so we're only talking about those who are in the waiting line, where L includes those in the waiting line and those in service. Then for our operating characteristics related to time, again, there's 2. And the first one is going to be, we're going to use the letter W, and think about the W standing for waiting. All right, W is the average waiting time, or average time that the customer spends in the whole system. And that's from the time that the customer enters until the time that the customer leaves. And W sub Q is the average amount of time that one customer spends only in line, not in service, so only in the queue. And then lastly, our probabilities. And the first one is that we're going to be interested in is this letter. This is not a P. This is the Greek letter rho, spelled R-H-O, and it's pronounced row, like the rowboat, row your boat, R-O-W. That's how it's pronounced. And it's the server utilization, all right? Or it's the percent of time that the server is busy, or you could say it's also the probability that a server is with a customer. What's the chance that a server is busy? There's many different ways to say this, but it really represents the server utilization. And then lastly, we're going to have the term P sub N, and that's going to be, we're going to be able to answer the probability that N customers in the system. So N can take on any value. N can be 0. Any positive value, I should say. It could be 1, it could be 2, and this includes customers. This is the probability of customers in the system. So this includes both those that are waiting as well as those that are in service. So let's think about this just for a minute. What does the term P sub 0 represent? And again, this is the case where n, what does P sub 0? This is the case where n equals 0. So P sub 0, then, if you're just reading the definitions, the probability of 0 customers in the system. So if you think about this another way, or express it another way, it's the probability that the system is empty, or you could say it's the probability that the server is not many different ways to explain this. And again, the other important thing is it's the probability that there are end customers in the system, which includes both in waiting and those being served. The next slide I'm going to show you just briefly, and I don't want you to worry about this yet, but these are the formulas given that we know our arrival rate and our service rate, and that we have the exponential distribution. We can calculate these operating characteristics using the formulas shown on this page. I'm not going to worry about this too much. You'll also see these formulas on page 206 through 208. We're going to stop this right now, stop this recording now, and then in the next recording for this lesson, I'm going to go through an example problem. And that example problem is problem 5.6 on page 217 of your textbook. It's Peachtree Airport. You type that out. Peachtree Airport. So go ahead and turn to that, or be prepared to turn to that before you watch our next video. All right, Peachtree Airport for the next problem.